So let's do some examples of calculating work and see what negative work means. Because remember, work is not a vector, but it is a scalar quantity and scalar quantities can be negative, right? Scalar quantities can be negative, like a negative temperature, for example. So just remember that we had actually done an example where we calculated the work done and we found the work done, right? Force times distance, 450 joules. So that's sort of a standard work problem. But let's look at some other examples. So let's say, for example, if I've got an object, let's go to the top of Martin Science Building and let's drop our book. And let's say that Martin Science Building is a height h, and ask how much work is done on the book when it's dropped. Well, done by what? Gravity is the only thing that's exerted on the book. So let's look at the book and say there's a force of gravity, that's a free body diagram, as the book falls. And so the work done on the book is done by gravity, right? So there's work done by gravity. So I'm not the only person who can do work on an object. Any force can do work on an object. And the work done by gravity in that case is what? It is the magnitude of the force, F sub g, times the magnitude of displacement, h, times the cosine of the angle between them. The angle between them. Well, is the displacement up or down? The displacement, h, is actually, or we could say displacement d has a magnitude of h in the downward direction, right? So what's the angle between the gravitational force and the displacement? That's where we need to look at our arrows. The angle between the gravitational force and the displacement is 0. So the work done by the gravitational force on the book as it falls is the magnitude of the gravitational force, mg, times h. What if instead of dropping off the building, I slide it down a ramp? Let's attach a ramp to the top of the building and slide it down a ramp. Let's say that the building is still h high, and I slide it down a ramp. Let's go ahead and draw a slide, and we'll just make it a straight ramp. And let's put that ramp at an angle phi relative to the ground, whatever that ramp is. And let's ignore friction and ask how much work is done on the book as it slides down the ramp from the top to the bottom. Work done by what? Well, let's draw a free body diagram of the book. Whoops, let's just go ahead and draw a free body diagram of the book. There's a normal force which is perpendicular to the ramp. There's a gravitational force which is straight down and no friction. So that's it. Those are the two forces. So say, so we can calculate the work done by the normal force and we can calculate the work done by gravity. What's the work done by let's start with the normal force. It's the magnitude of the normal force times the magnitude of the displacement times the cosine of the angle between the normal force and displacement, which is not phi, at least not necessarily. But what we didn't draw is we didn't draw in the displacement, right? The displacement is, it starts at the top of the ramp and it goes to the bottom of the ramp. So right there is my displacement. That's my d, displacement. Now careful. Fn, the normal force is in this direction, displacement's down the ramp. What is the angle between Fn and d? Angle between, for Fn and d, is what? It's 90 degrees. Right? Fn is perpendicular to the ramp and d is parallel to the ramp, so it's 90 degrees. So what is the work done by Fn? The work done by Fn, and you probably should have been able to see this, is 0 because the cosine of 90 is 0. But we can also say, the work done by the normal force is 0 because the normal force doesn't move the object. The normal force can move the object, but in this case it doesn't move the object because what's moving the object is the gravitational force pulling it down the ramp. The normal force has no part in that. So the work done by the normal force is 0. Then the work done by gravity. Let's see what the work done by gravity is. It's the magnitude of the gravitational force times the magnitude of displacement times the cosine of the angle between them. And now I'm going to, I'm going to just say theta. I'm going to actually write this on a new page. Careful, because this angle is always a different angle. It's not just one angle in the problem. In this case, it's the angle between FG and D. It's always the angle between these two vectors. Okay, so we know that the Magnitude of the weight is mg. What's the magnitude of displacement? Ooh, shoot. We don't know the magnitude of displacement, but we do know that the building was h tall. And that was a given, right? So we can write that h equals d times sine of theta. That's just looking at the triangle. H equals d sine theta. So d is h over sine theta. Sure, I know that some of you still need me to spend a little time on this. When I say h equals d sine theta, that just came from the fact, not theta. Nah, there is no theta here. Ooh, good thing I came back to this. Phi, this angle, which I called phi, because theta we're currently reserving for the angle between the two vectors in work. How did I know this? I knew this because I could just write the sine of phi is the opposite over the hypotenuse. The cosine of phi is the adjacent, which I don't know, over the hypotenuse. And the tangent of phi is the toa, O over A, H over A, right? We can just write SOHCAHTOA and then solve, right? In this case, this is the one that has H and D in it, so we can get a relationship between H and D. You can always get a relationship in a right triangle. Okay, so H over sine theta and cosine of the angle between FG and D. Now, FG is down, the gravitational force is down, D is straight down, D is down the ramp. So let's go ahead and draw that picture. Cosine of theta, this was phi, and cosine of theta, where D points along the ramp and MG points in this direction, so the angle between them is right there. It's not phi. Do this geometry here, and I know for some of you it's going to be a bit tough, but phi is that ramp angle. Theta in this case is this angle here. So this is the theta that we're interested in for the direction, the angle between MG and D. And do a little bit of geometry and you will find that the cosine of theta is equal to the sine of phi. That is true. So therefore, what is the work done by the gravitational force? The work done by the gravitational force is mg h times the cosine of theta over the sine of phi. But we found out they're the same thing. So it's just mgh. Now, where did I get this from? This is understanding the geometry of the right triangle. You can think about that. You can look it up. You can do what you want. But it is true because of the right triangle that is right here. And what we get is the work done by gravity is mgh. Look, it's the same work done by gravity as if we dropped the book straight off the building. Gravity still does the same amount of work. So interesting. Shouldn't be such a surprise because it's just like the rope problem we started with. When we're moving a piano, we can reduce the force by increasing the distance that we pull. And that's what we're doing here. We're reducing the force that's pulling the box downwards, but we're increasing the distance such that the force times the distance is always a constant, mgh. So you don't even have to worry about this phi if you understand that the work done by gravity is always the magnitude of the gravitational force, mg, times the displacement in the direction of the gravitational force, h. That's the displacement downwards. It says, this is actually a result, but it's a result that comes up so frequently that we actually use it like it's a formula. We say that the work done by gravity is always the gravitational force, mg, times the displacement in the downward direction. You have to know, if you're going to use this formula, that h means displacement in the downward direction. Now, what do I mean by downward direction as opposed to upward direction? This is where we can talk a little bit about negative work. What if I lift the body up? I take a book, I pick it up off the ground, and I pull it up a distance h. So I'm going to lift, F lift. My arms and hands are hard to draw. So I'm just going to lift it up. What is the work done by the lifting force? The work done by the lifting force? What's the minimum work done by the lifting force? What's the minimum force, right? I could exert any force to lift it. What's the minimum force that I would have to exert to lift it? It's the gravitational force, right? That's the minimum force, mg. So if I lift something a distance h, then the work done by my lifting force is mgh. What's the work done by gravity? Careful. Let's draw a free body diagram. The free body diagram of the object as I lift it has F lift in the upwards direction. It has F gravitational in the downwards direction. And my displacement is in the upward direction. So that's not part of my free body diagram, but in order to calculate work, I got to know my displacement direction. So the work done by gravity is the magnitude of the gravitational force times the magnitude of the displacement times the cosine of the angle between them. The magnitude of the gravitational force is mg. The magnitude of displacement is still h. But what's the angle between this force and this force? The angle between those two forces, right? Because this is the angle between FG and D. Angle between those two forces is 180 degrees. This is minus mgh. The work done by gravity when I lift something up is negative. What does that mean? Does that mean that it's in the negative direction? No, it doesn't. Because I haven't defined a direction. This is so important, and I will ask you this on an exam. I have not defined a direction here. Didn't have to do this problem. Right? The work done by gravity is negative because gravity is working in the opposite direction of the displacement. Remember that work is the magnitude of the force times the magnitude of displacement in the direction of the force. Well, the magnitude of the displacement in the direction of the force here is essentially minus h because it's not in the direction of force, it's in the opposite direction. What does a negative sign really mean for work? What a negative sign means is that the force is trying to move it in the opposite direction. It means that the force is trying to slow it down. It means I'm moving it in the upward direction, gravity is trying to pull back. So if your force is in the same direction of displacement, you get positive. If the force is in the opposite direction of displacement, you get negative. That's what it means. It just tells you about the relative direction of the force versus the displacement. And what it also means, which we'll see in a second, is that a positive work wants to speed a body up, a negative work wants to slow a body down. That should make some sense here. So let me ask one more question. Let's say that I go ahead and drop my book off the top of the building. I drop my book off the top of a building, height h, and then I go and I pick it up, and then I run up the stairs and I bring it back up to the top of the building again. So 1, 2, 3, right? So the book starts at the top of the building and finishes at the top of the building. Question is what is the total work done? Or let's just ask, what's the work done by gravity for the whole trip? What's the work done by gravity for the whole trip? The work done by gravity on the way down is mgh. The work done by gravity on the way up, even though I didn't travel a straight path, right? We already showed that the work done by gravity is independent of path. That's an important thing. It's independent of path. And it's on the way up, it's going to be minus mgh. So what's the work done by gravity? If I start and finish at the same place, 0. The total work done by gravity, no matter how you get from one point to another point, is equal to mgh, where h is the vertical distance in the downward direction. So if I start and finish at the same place, then h is 0. You could also make the same argument, as long as I start and finish at the same place, that whatever force I exerted on it. No, sorry. I was going to say something that wasn't true. Actually, I only lifted it from 2 to 3. So I did, so I lifted it mgh. I exerted a lifting work of mgh in the upward direction. But for that round trip, the thing I was trying to get at is for the round trip, the work done by gravity was 0.